So very warm welcome to the second of this afternoon's Oxford Discrete Maths and Probability seminars. So it's a huge pleasure to have Shalom Letzter, who's going to be talking about an improvement on Woodchuck's connected matchings method. Thanks very much, Shalom.
Okay, so thank you for the invitation and thank you all for coming. So I'll be talking about the topic in Ramsey theory. So let's start with some definition. So I write G arrows H for graphs G and H. If whenever I red blue color the edges of G, I get monochromatic, so either red or blue copy of H. So for example, as you may all be aware of, K5 does not arrow K3 because there is a red-blue coloring of the edges of K5 that does not have a red triangle or a blue triangle. But K6 does arrow K3 because whenever we read blue K6, we can find a monochromatic triangle. Okay, and with this definition, the Ramsey number of a graph H is the minimum n such that Kn arrows H. So for example, with this triangle example, the Ramsey number of a triangle is 6 because K6 arrows K3, but K5 does not. And kind of central question in Ramsey theory is to determine this Ramsey number of a complete graph, which is obviously very interesting, but this is not really what I'm going to talk about. Instead, here is a more relevant result to this talk. So this is an early result of Geranger and Garfash from 1967, and they looked at the Ramsey number of a path. And they showed that the Ramsey number of paths of length n is roughly 3n/2. And here's an example that shows that indeed you cannot go lower. So this is a graph on about 3n/2 vertices, and we can see that the blue graph, well, it only touches n vertices, so it does not have a path of length n. And the red guy, any red path, has to kind of every 2 steps has to go through this small bit, so it consists of at most 2 times the size of this plus 1. So again, it does not have a red path of length n. Okay, so having seen this, obviously one should ask, well, what should we be thinking about next? And one thing to consider is, well, what can we say when there are more colors? So here are just the same definitions from the previous slide, but for S colors. So I will say that G S arrows H if in every S coloring of G, there is a monochromatic copy of H. And the S color Ramsey number of a graph H is the minimum n such that Kn S arrows H. And our question becomes, well, what can we say about the S color Ramsey number of a path? Okay, so here is again the result of Geranger and Garfash, who answered this question for S equals 2. But now we want to say something about larger S's. So firstly, here is a lower bound. So to see this lower bound, I just need to give you some constructions. Here is 1, so this will be for S equals 4, so for 4 colors. And so I will have roughly 3n vertices, which I divide into these 6 sets. And you can see again, as before, there won't be a red path of length n because each red path has to touch a small, like this small blob or this small blob in every 2 consecutive vertices. And then, okay, we can rotate this picture. So same thing holds for green and blue. And the remaining guys are these pink guys. And again, the pink guys, each component only touches n vertices, so it does not have a pink path of length n. So this is one kind of relatively recent example, which shows that you cannot do better than S minus 1 times n. And there's also this affine plane example that works for maybe not every S, but many S's. And in particular, it works for S equals 4. And here, 2 colors. So you can see just the components are too small to accommodate a monochromatic path of length n. And here are the remaining 2 colors. Okay, so we have this lower bound, and then kind of well-known easy upper bound is that the S-color Ramsey number of path length n is bounded from above by Sn plus 1. And this follows from this Erdős-Galai theorem, which is essentially a Turan result for paths. So it says that if a graph has average degree at least d, then it contains a path, average degree at least k, then it contains a path of length k. And with the setup, so suppose you have a complete graph on this many vertices and you color it with S colors, then one of the colors will have average degree at least n, and so it will have a path of length n in that color. Okay, so we have these 2 bounds, which are relatively close to each other, I guess. And I would say that it is believed that the S-color Ramsey number of the path is roughly close to what this lower bound suggests. And here's some evidence for this. So a result of Figa and Wuczek says that the 3-color Ramsey number of path of length n is roughly 2 times n. And a more precise result followed shortly after by Giafra, Shrusinko, Sarkozy, and Samradi. They determined that it's 2n or 2n plus 1, depending on parity. Okay, and you may have noticed, well, these results are from early 2000s, and the previous result that I mentioned is from 40 years earlier. So yeah, why is there such a big gap? And the reason is basically this missing link. So this was an idea of Wuczek, which appeared in the late 90s, which kind of gave a convenient way of thinking about Ramsey numbers of paths and cycles. Basically, what he showed is that they can be reduced to Ramsey type problems about connected matchings. Okay, so maybe I should tell you what a connected matching is. So here is the definition, it's very simple. A connected matching is a matching that lives in a connected component. So here's an example. Well, a matching is just a bunch of vertex disjoint edges. So here, these gray edges form a matching. And I say that this matching is connected because all of these edges live in the same connected component. And now if I add another edge from another component, it becomes, well, it's no longer a connected matching. Okay, so this is a connected matching. Now I want to talk about Ramsey, I want to talk about colors, so I should think about this notion of a monochromatic connected matching. Well, this is a matching that is contained in a monochromatic connected component. And here's an example. So here is a like red component and the matching contained in it. So it is a red connected matching. And just to clarify, when I'm talking about the vertices or edges of a connected matching, I'm thinking about the matching itself, not the component. So this guy is a red connected matching on 6 vertices, even though it lives in a larger component. Okay, and a definition, Cm of n, connected matching of n, is the family of connected matchings on at least n vertices. Okay, and now we want to relate connected matchings to these problems about paths and cycles. So here's a very deep observation. Suppose I'm given a path of length n, then within it I can find a connected matching on at least n vertices. For example, here a path of length 6 and a connected matching that covers 5 vertices. Right, so there may be a parity issue, hence the move from n plus 1 to n. Okay, so using this very deep observation, we get this, this connection between Ramsey problems about path and Ramsey problems about connected matchings. So if Kn S arrows a path of length n, then we know that it also S arrows a connected matching on at least n vertices, which means, by which I mean that in every S coloring of Kn, there is a monochromatic connected matching on at least n vertices. Okay, so this was really a trivial observation. But the interesting thing, which is what Wójcik showed, is that in some sense, the converse of this observation holds or almost holds. So to see what I mean, here is a lemma of Figai and Wójcik, who essentially just formalized an idea that appeared earlier in this paper by Wójcik. So here's what it says. It says that if for every epsilon and large enough n, so if for these epsilon and n, every almost complete graph G on slightly more than alpha n vertices S arrows a connected matching on n vertices, then the S-scalar Ramsey number of a path of length n or n vertices is at most about alpha n. So again, I guess my aim is to have some control over these S-scalar Ramsey numbers of path. So this is my goal. I want to show that the S-scalar Ramsey number of path is bounded by roughly alpha n. What this lemma tells me is that it is enough to show that for every graph on slightly more vertices, which is not quite complete, but almost complete, like the same thing holds, but for connected matching. So instead of having to find a path, I need to find a connected matching, which obviously, if I found a path, I immediately automatically found a connected matching. So you can imagine that finding a connected matching should be easier. Okay, so now I thought I would sketch the proof of this. It's not really kind of crucial for this talk, but I thought it might be interesting. So yeah, the proof uses the regularity lemma. So here is a very imprecise statement of the regularity lemma. It says that given any large graph G, its vertices can be partitioned into not too few or too many parts. So here are these parts of equal size, V1 up to Vk, such that for almost every pair of like sets Vi, Vj, the graph between them is random-like. Okay, so again, I start with a large graph, and this regularity lemma tells me that I can partition its vertices such that essentially I can think of my graph as being this union of random graphs. So here is the random graph, maybe with some parameter. Here's a random graph with another parameter. And for just very few of these pairs, we cannot really say anything intelligible. But for a kind of global idea of what G looks like, it's sort of like this joint union of, or this union of random graphs. Okay. So now I want to prove this. I want to prove that if every almost complete thing arrows a connected matching, then something similar can be said about paths. Okay, so I'm going to suppose that this assumption holds. So every edge which is almost complete on some number of vertices, S arrows a connected matching on n vertices. And now I'm going to take a graph G, which is an S-colored complete graph on capital N vertices. And okay, so I want to show that this G S arrows a path of a certain length. So I'm going to apply the regularity lemma to G, and I obtain this partition, this regularity partition. Now I'm going to form an auxiliary graph. So instead of thinking, so I no longer think of individual vertices of G, but I think of just these clusters. And I want to just model how they look like. So my vertices will be 1 up to K, which represent these these blobs. And my edges are edges ij such that the graph between vi and vj is random-like in all colors. And I'm going to color ij by the most common color. So say this guy I know is random-like, and I just color it by the most commonly occurred color. Okay, so the point of the regularity lemma is this H is almost complete. That's what the regularity lemma says. So it says that almost every pair behaves very nicely. Okay, and now I'm going to look at this graph H. And I know from the assumption that it S arrows a large connected matching. So here is my large connected matching. So these two edges, red edges, they're form matching and they live in a connected component. And the point is that I can now lift this connected matching that lived in this auxiliary graph H to a path which covers about the same proportion of vertices in G. And the way it works is just, I say, well, look at these fat edges of the matching. I can, because it's the graph between them is random-like, I can find a path that covers almost everything here. And again, a path that covers almost everything here. And because the matching is connected, so that's why I need connected, I can join these two things to form a cycle or a path. Okay, so this was just a sketch of this idea of turning questions about finding monochromatic paths to finding monochromatic connected matchings. And here is the lemma that formalizes this again. Now, as you may imagine, there are some applications of this. Obviously, I already stated a couple of applications about the 3-color Ramsey number of path. But here are some more. So, for example, the recent result of Knierim and Su establishes the currently best known upper bound on the S-color Ramsey number of path, which lies nicely between these two easy bounds that we saw before. So we saw that the we saw that the S-color Ramsey number of a path lies between S minus 1 times n and S times n. And what they showed is that you can get an upper bound, which is the average of these guys. So the best known upper bound in general is S minus half times n. And actually the exact same idea holds for even cycles, because maybe you noticed in the previous slides, it's essentially as easy to get a cycle as it is to get a path, but there is some parity issue that, which is the reason why we need to require even here. And actually for odd cycles, quite a lot more is known. So actually very nice result by Jensen and Skok, and they determine the S-color Ramsey number of an odd cycle precisely for every large n. And well, I didn't write it here, but it's also kind of interesting that you genuinely do need this large n, probably not quite as large as they have it, but it's not true for every n and s. And pretty much every other Ramsey type result for paths and cycles from the last 20 years or so uses this, maybe not this lemma, but this idea of Wojcik. Okay, but has this kind of obvious drawback that instead of thinking about complete graphs, I need to think about almost complete graphs. And at the very least, this is annoying. So how one often approaches these things, you just think about what happens in complete graphs, you get the result, and then you just translate it into something for almost complete graphs by just introducing an epsilon and running through the argument, which obviously makes things yeah, I'm very sorry about this. So it is at the very least annoying to have this epsilon, but actually it also introduces a genuine difficulty. Like you cannot really use induction with almost complete graphs. And yeah, so this is a drawback. And this is what I want to address in this talk. So basically, my result says that you can kind of circumvent this almost complete issue, and you can show that exactly the same thing, essentially, except for we don't need to consider almost complete graphs. It's enough to consider complete graphs. So what I show is that if the complete graph on slightly more than alpha n vertices S arrows a connected matching on n vertices for every large n, then the same holds for path. So in other words, the S-Caylor-Ramsey number of path is bounded by roughly alpha n. Okay, so a few remarks about this. I kind of stated it in this particular form, but I can prove something a bit more general. So for example, I can allow for an asymmetric setup where you may ask for different lengths in different colors. You can also have cycles instead of path, but there is again this issue with odd cycles. So that makes the statement just a bit more complicated. And then you may want to look, instead of having your host graph be a complete graph, you can have it be a complete bipartite or a complete multipartite, or quite generally a blow up of any small thing that you like. Yeah, and finally, I should remark that with Matija Bucic and Benny Sudakov, we kind of implicitly proved a version of this, but for complete bipartite graphs. And I'll hopefully say a bit more about this thing later. Okay, so what I want to do in the rest of the talk is talk about the proof of this, basically. So I need one tool, which is this convenient kind of structure theorem about matchings. Okay, so given a graph G, well, Galay and Edmonds suggested to look at these two sets. The set B, which is the set of vertices that appear in every maximum matching of the graph G, and D, which is the remaining vertices, so vertices that are avoided by at least one maximum matching. Okay, so here is a graph, and for illustration, I drew two maximum matchings. There are more than that. And you can see that the vertices in B appear in both of these maximum matchings. But for example, this guy is avoided by the red matching, and this guy is avoided by the pink matching. Hence they are in the set D. Okay, and now they also looked at the refinement of this. So A is the set of vertices in B, so they are in every maximum matching, but they send an edge to the outside world. So they send an edge to D. And C is the vertices that lie in B, but do not send an edge to the outside world. Okay, and well, the interesting thing here is that these sets A, B, C, and D are kind of a useful thing to look at. And the reason is as follows. So for every maximum, what Edmonds and Galay showed is that for every maximum matching M in the graph G, firstly, when you consider just what happens on C, then M induces a perfect matching in this graph. So for example, here you can see that both red and pink matchings form a perfect matching in C. Next, something similar happens in D. So the maximum matching N induced on D covers all but exactly one vertex of each component in this D. So if I look at this D and I look at the pink or red edges that lie in here, then you see, well, this is a component of size 1, so it doesn't see any edges. And this is a component of size 3, and each of these red and pink guys, they cover all but one. So the red covers all but this guy from this component, and the pink covers all but this guy. Very good. And finally, about A, so the matching M matches the vertices of A to distinct components of D. Okay, so here, this is a bit of a degenerate example for this third bullet is each of these matchings send the vertex A to some component in D. Okay, so here is the same content, but a bit smaller. And here's the lemma that really that's what that would be my takeaway from this Edmonds-Galley theorem. So it says the following: suppose that G is a maximal graph on a given number of vertices, which does not have a matching of given size. Then the lemma tells me that G is a complete blow-up of a star. So a complete blow-up of a star is what you get by taking a star and replacing each vertex by a complete graph. And you're also allowed, so you're allowed a kind of degenerate case where the central vertex is an empty set. Okay, so this is the lemma, and to see a proof, suppose that, well, given my graph G, let me define A, C, and D as above. And then I claim that by maximality, my graph G will look like, well, this, like a complete blob of a star. So the point is I can add any edges I want to C, for example, can add any edges I want to A, any edges within the components of D, all edges that touch A. And I won't change the size of the maximum matching. And this kind of, I won't explain exactly, but this just follows from this structure result of matching. So when you think about how a matching will look like here, it will essentially look exactly like what is written here. And so you won't be increasing the size of the matching. Okay, yeah, so what we need to remember is that if you're maximal with certain number of vertices and without a matching of certain size, then you look like this. Very good. Okay, so now I want to kind of move on to prove my theorem. Okay, so I want to prove that if a complete graph on alpha n plus a bit S arrow is a connected matching on n vertices, then the same holds for a path with slightly smaller number of vertices. Now, I'm not going to go through the regularity lemma or anything like that. Instead, I'm just going to use this lemma as a black box. So you can see that they both have the same conclusion, that the scalar empty number of a path is at most about alpha n. And so it suffices to show that the assumption in my theorem implies the assumption in their theorem. So all we have to do is to show that if something happens in complete graphs, then something happens in almost complete graphs. So more precisely, this is what I need to show. So I'm going to show that if K subcapital N S arrow is a connected matching on n vertices, then for every epsilon, positive epsilon, there is a positive delta such that if G has capital N plus a bit, so plus epsilon n vertices, and every vertex in G lies in at most delta n known edges. So this is slightly stronger than saying that G is almost complete, but essentially good enough. So I'm assuming that basically the degree is almost full, but not quite. Okay, so I'm going to show that in these conditions, it will follow that G S arrow is a connected matching on n vertices. Okay, yeah, so this is what I need to show. Here it is again. Okay, so yeah, so my assumptions as written in the previous slide, K subcapital N S arrow is a connected matching on n vertices. I'm going to fix an epsilon. I'm going to let delta be much smaller. I'm going to take a graph G on slightly more vertices, where every vertex is in very few known edges. And I want to show that G S arrow is a connected matching on n vertices. So let's assume the contrary, and let's fix some bad S-scalaring. Okay, and yeah, now I just need to reach a contradiction. Okay, so instead of working with this graph G, I'm going to work with this graph G1, which contains G, but it's also maximal with respect to this not having monochromatic connected matching on n vertices. Now it's going to be convenient for me to assume that to let this G1 be multicolored. So every edge has a color, but maybe it has more than one color. Okay, and to understand how to form G1, just think like fix one color, say red. So I know in G, the red graph in G does not have a connected matching on n vertices. So I'm just going to add as many red edges as I can while maintaining this property, and eventually, well, I will not be able to add any red edges, and then I repeat this for every color, and this will be my G1. Okay, very good. So why is this useful? Well, let's see some properties of G1. Okay, so this first thing just says that every vertex in G1 is in a small number of non-edges, and this holds just because G1 contains G and has the same vertex set. Next, a kind of slightly less trivial observation: in every color, there is at most one small component, because if I had two components on less than n/2 vertices, I could add an edge between them. Yeah, so this is here, it is convenient to have this multicolored, so I don't have to worry about other colors. Okay, so in every color, there's at most one small component, which implies that the number of components in each color is small. Okay, and finally, this is a consequence of my lemma from a few slides ago. Every monochromatic component looks like this, looks like a complete blow up of a star. And just to have some notation, I'm going to call this center of the star the head of U and denoted by H of U, and the rest will be the tail of U. Okay. And here is where how to finish the proof. So I'm going to take M to be a maximum or maximal matching in the complement of G1. So I'm looking at the same vertex set, and I'm just taking a matching of non-edges. And this claim tells me that the size of M is small. So we'll talk about why this holds later, but for the moment, let's believe this claim. So M is a maximum matching in the complement of G1, and I claim that this matching is small. What I'm going to do is just look at this graph G2 formed by taking G1 and removing the vertices of the matching. Yeah, so this G2 is formed by removing the vertices of the matching of this matching of non-edges from G1. So what can I say about G2? Well, firstly, since I didn't remove too many vertices from G1, it still has many vertices, namely at least n vertices, right? So G1 had n plus epsilon n vertices, M had at most epsilon n over 2 vertices, and so I get, that G2 has at least capital N vertices. G2 is complete, because if G2 had a non-edge, then I could have added it to M to get a larger matching. And finally, G2 does not have a monochromatic connected matching on n vertices, because G1 did not have one and G2 is a subgraph. But this is a contradiction to our assumption. So we started off by assuming that the complete graph on n vertices S arrow is a connected matching, and we now formed a graph which is complete as colored or as multicolored and does not have a monochromatic connected matching on n vertices. Yeah, so this proves the theorem, and all that remains is to prove the claim. And I see that I have plenty of time, so let's look at the proof of the claim. So for this, I will need the notion of a type. So for each vertex, a type will tell me in which monochromatic components it lies, and also whether it lies in the head or the tail of the component. So more precisely, tau of U is the sequence U1 up to US and alpha 1 up to alpha S, where alpha I is the color I component that contains U. And alpha I is H if U is in the head of UI, and it's T if U is in the tail of UI. Okay, so a type basically describes what a vertex looks like in some sense. And the observation is that the number of types is small. So small in sense, well, I think of the number of colors as being fixed and didn't really mention it, but capital N, I can think of it as small in terms of N. So there's a small number of types. Okay, so I want to prove the claim. So let's take a matching in the complement of G1. My aim is to show that the size of the matching is small. So let's suppose it is large. Now I can do a kind of pigeonholing argument. So I know that each edge in M has this pair of types for the two ends of M. So I'll just take the most popular pair of types. So let this be, these two types be tau and sigma. And I take M0 to be the submatching of M, whose edges have ends of types tau and sigma. And I find that because the number of types is small and delta is much smaller than epsilon, that M0 is pretty large. And I'm going to think of M0 as having two sides, the side X, which consists of type tau vertices, and side Y, which consists of type sigma vertices. Okay, yeah, so I have this M0 and now I want to get some contradiction. So here is my plan. So given, I start off with this M0 and I'm going to define a sequence of submatching M0, M1 up to MS, where each of these MIs is a submatching of the previous matching MI minus 1. And okay, they're all kind of large. So MI is at least the size of M0 times 4 to the minus I. And there are no I-colored edges between the two sides of MI. Now with these two conditions, if I look at MS, then firstly, the two sides of MS are large, have size at least delta n because of this bullet and because of the first bullet here. And I find that there aren't any edges between XS and YS because there are no I-colored edges between these two sides for every I. And so, yeah, and so there are no edges. But this is a contradiction to my assumption that every vertex in G1 was in a small number of non-edges, right? So again, I found two sets XS and YS, which are larger than delta n, and there are no edges at all between them. And so, yeah, contradicting my assumption. Right, okay, so I have my M0, which consists of a matching of non-edges between type tau vertices and type sigma vertices. And I want to form, basically all that remains is to find these submatchings MI. So suppose that I already found my MI minus 1, and I want to find within it a matching that decreases, whose size decreases by at most a factor of 4, and such that there are no I-colored edges between the two sides of MI. Right, and here are my two types, tau and sigma. Okay, so this is basically once you've reached this point, you just do a kind of simple case analysis as follows. So I'm going to look at two cases. So UI is the component which contains all the type tau I-colored component which contains all the tau type vertices. And WI, same thing, but for sigma. Yeah, so case one is when these two components are different. This means that the two sides of mi-1, so xi-1 and yi-1, lie in distinct I-color components. And so there are no I-colored edges between them at all. And so I can just take mi to be mi-1, right? So I just automatically get this condition that I want, and that there are no I-colored edges between the two sides. Okay, very good. Now, obviously, we should look at the case where everything lies in the same component. And then I claim that if everything lies in the same component, then everything has to lie in the tail of the component. And the point is that if I just live in this component, the vertices in the head aren't incident to any known edges, like they're connected to everything. But I chose mi-1 to be a matching of known edges. So that's, yeah, that just wouldn't work. Right, so again, like every vertex, just by choice of mi-1, every vertex in mi-1 is incident to a known edge in this component. And so everything has to live in this tail part. Okay, so here is the situation again. Everything lives in some component, I-colored component, which I call U. And in fact, everything has to live in the tail of U. So we should take a closer look at the tail. It consists of these disjoint cliques, K1, K2, K3, and so on. And now I want to define my new matching. So here's a kind of standard little trick. I'm going to just toss a coin for each of these KIs to decide if they go to this orange bit denoted by A, or if they go to this pink bit denoted by B. Okay, and I'm going to take mi to consist of these edges from before. So I started with some mi-1. And then I keep only those edges in mi-1 that go across between these two blobs. And it should be easy to check that the expected size of this new matching mi is exactly the size of mi-1 over 4. So I can find some matching that has at least this size. And also, well, the important thing is that there are no I-colored edges at all between these two sides, A and B. And so there won't be any I-colored edges between the two sides of mi. And that's it, right? So this was kind of our goal here, which gave me this sequence of mi's, which is what I needed for the claim. That proved the whole theorem. Okay, so this is essentially it about the proof. Now I want to make a few more remarks about this, my theorem. Okay, so here it is again. And as I mentioned, I phrased it here in this kind of relatively simple setup because it's just easier to talk about it, but it holds in a bit more general setting. And in fact, so the way it's phrased, it's kind of handy to prove upper bounds on Ramsey numbers of path, but it can also be used to prove stability results, which look something like this, which say something like for every S coloring of some complete graph, either I can find my monochromatic path as I want to, or the coloring has some very particular shape. And these stability results tend to be the kind of necessary step to go from something kind of asymptotic, so something with this little error term, to something more precise. Yeah, so just the good news is that it's like this idea of going from almost complete to complete works not only for getting these asymptotic upper bounds, but also hopefully they can be used for more precise bounds as well. And something which I didn't really want to introduce this notion very precisely, but actually it turns out to be convenient sometimes to look at fractional matchings, which you can imagine what it means, but actually for fractional matching in a graph, all you need to think about is a collection of, you can think about it as being a collection of vertex disjoint edges and odd cycles. So a normal matching is a collection of vertex disjoint edges, and in fractional matchings, you just need to add odd cycles, and somehow that's, yeah, that adds, like, in some sense, it doesn't, like for the Woodchuck's method, it doesn't really matter. So you can think back about the proof that I gave for Woodchuck's method, that like everything would work the same. Oops. Yeah, sorry, there's a slide missing. Anyway, yeah, the point about fractional matchings that I tried to make, but didn't manage, is that they have a much nicer structure theorem. So we saw this Galai-Edmonds theorem for matchings, and if you work in the context of fractional matchings, and you actually get something that is more convenient to work with. And so far recently it has been used a little bit, and sometimes it genuinely provides better results. So yeah, just if you're thinking about these type of problems, then it's worth it to look at fractional matchings, and also useful to note that this stuff also works for fractional matchings. Okay, yeah, so I mentioned before this result with Mattia and Benny Sudakov. And what we did there is we, again, had a kind of Ramsey type result, but for bipartite graphs. So we showed that if we look at the complete graph, or complete bipartite graph on 2n vertices, complete balanced bipartite graph, where capital N is roughly 3n/2, then this thing, 3 arrows, a path of length n. Okay, so here's an example that shows that this is kind of best possible. So I have a complete graph, complete bipartite graph on sides 3n/2 and 3n/2. And you can see here that the largest monochromatic path has length roughly n. Okay, and we showed that this is essentially best possible. And the way we started thinking about it is well known. It's good enough to think about connected matchings, but somehow for us it was convenient to do induction, and so we managed to prove this result, but for connected matchings. And then we wanted, well, our aim was to prove a result for path. But we had this inductive proof, and normally you kind of want to have, well, you want to go to something that is almost complete, because this is how Woodchuck's method works. But yeah, we just didn't find a way to convert our proof to work for the almost complete setup. And so we came up with a version of this. And somehow since then, I realized that this might be a useful thing to have more generally, but didn't immediately see how to do it until now. Okay, yeah, so this was kind of born out of necessity, is what I'm trying to say. Like, we genuinely needed this stronger version of Woodchuck's method. And then I realized, well, maybe it's a good idea to prove it for the more general setup as well, rather than this bipartite setup. And indeed, well, this is not exactly an application, because this is something that was known, but just to kind of test this idea, it's if you try an inductive approach for this 3-color Ramsey number of a path, then you can get an easier proof of this result. Yeah, so hopefully some more applications will follow. Now, yeah, obvious open problem is to determine the S-scalar Ramsey number of path. Doesn't look very easy, but hopefully will be useful that you can now look at complete graphs. So maybe an inductive proof, I don't know. And a different kind of question. So here, in some sense, we have a pretty general result, which shows us that it's good enough to look at complete graphs, but there are some other setups. I gave here an example of monochromatic cycle partitions, where our aim is to cover the vertices by as few as possible vertex disjoint monochromatic cycles. And I thought about it a bit, and it's not obvious like that the almost complete setup can be translated to complete one, but might be nice if it does. And there are other things, like sometimes one might be interested in looking at not just the longest path, but the two monochromatic paths that cover together as many vertices as possible. And again, this doesn't seem to work as nicely, but might still be true. Yeah, so that's it. Thank you.
Thank you very much, Sean. Can I invite people to ask questions either in the chat or raise your hand, and I can unmute you. So Alex says he's got one, so Alex, feel free to unmute.
Yeah, thank you, Shem, for very nice talk. Can you say a little bit more about the vertex disjoint monochromatic cycles and what you might hope for, either for covering everything or
I'm not sure, to be honest, what the right statement would be, but like, I mean, but the same idea of moving to using regularity lemma to, I guess I see what the question may be. Like, using regularity lemma, we kind of can say if we can cover almost all of the vertices of an almost complete graph by monochromatic cycles, then we can do the same in a complete graph. So there's this almost all vertices rather than all vertices, which which is something that is kind of unavoidable by applying regularity lemma, I guess. But I guess maybe I want a statement like, if in a complete graph, I can cover almost all of the vertices, or maybe all of the vertices, by just monochromatic connected matchings, by some number of monochromatic connected matchings, and the same hold for almost complete. I don't really know, but the issue is that here, instead of just the size of something, you care about exactly which vertices you cover, and so it's hard to add, like, do this, take a larger graph without kind of ruining things.
But is the thought somehow that you'd use the monochromatic matchings to absorb some small fraction of badly behaved vertices?
I'm not sure. I mean, this is something that you would need to do anyway. I guess my hope, I mean, I'm not sure what exactly my hope was, but I guess what would you do now? You would like apply regularity lemma, and then you get this almost complete graph, and then you think about connected matchings, and then maybe you can show that you can cover absolutely everything by 3 monochromatic cycles. But of course, when you go back to your original graph, you may have to do some absorption. Maybe the absorption is like a separate thing. But I guess in this, when you do this, you still have to think about almost complete rather than complete after you applied regularity. So maybe my hope is that just to avoid this almost completeness, I guess, but not like avoiding this absorption. I think that's a different type of step. But anyway, I mean, I don't know how to do that anyway, so I'm not sure.
Are there any other questions? I can't see any in the chat. I think in that case, I'm going to press stop, and then I'm going to invite everybody to unmute themselves and to give Sherm a big round of applause.